Imagine driving home at night, stuck bumper to bumper on a highway that isn't moving. Right next to you is a perfectly maintained, totally empty road, but there are no exit ramps, so you can't use it. Electricity on our power grid behaves exactly like those trapped cars. Electrons naturally flow down the path of least resistance, and without a traffic cop to direct them, they'll cram onto the easiest route until it jams. This map illustrates the result of that missing traffic control. Right now, the United States power grid operates at about 50% of its physical capacity. Because we can't actively route power, certain lines are pushed to their limit, while neighboring lines sit unused. This traffic problem is the primary hurdle in our transition to clean energy. We have to move massive amounts of power from where it's generated to the cities where people actually live. The challenge is that vast wind and solar farms are usually located hundreds of miles away from those major population centers. When we try to force thousands of megawatts of new clean energy into an aging, unmanaged network, the system overheats. The physical wires become so saturated that they heat up, sag, and eventually snap, triggering local blackouts or dropping embers that can start wildfires. For decades, the only way to solve this was to spend billions of dollars building massive new steel transmission towers, a process that requires years of permitting and construction. But we already have thousands of miles of wire. We don't need to build a second identical highway. We need to give the highway we have a brain. This simulation model, a 9-point virtual network, helps engineers identify weak spots. Zooming in on this bottleneck shows why the grid fails. Line 3 is choked at over 91% capacity, while neighboring Line 2 rests at just 36%. In a traditional grid, operators have no physical way to move that heavy traffic off the red line and onto the blue line. This local imbalance limits the entire region. Until the load is shared, clean energy sits waiting, unable to reach the homes that need it. To solve this, engineers developed smart wires. These modular devices clamp directly onto existing transmission towers to act as physical traffic controllers. This schematic details how they work. In push mode, the device adds electrical resistance to the wire, forcing electricity to find a different path. In pull mode, it does the opposite, drawing the detoured electricity directly into unused lines. By pushing and pulling at the same time, the flow across the entire network evens out in real time. The bottleneck vanishes. We are now routing thousands of volts of physical power with the exact same precision your home router uses to manage data bandwidth. This chart shows the macro impact of that routing. By distributing the load, we can increase our grid's capacity by 30% without new wires. Because we maximize existing assets, this upgrade costs less than half as much as traditional construction. This technology is currently being deployed across the United States, Europe, and South America to keep up with the rising demand for renewable energy. This approach, equipping wires with sensors and controllers so they can monitor their own state, is spreading beyond the power grid to solve similar problems in high-stakes environments. In aerospace, miniaturized versions of this tech act like a nervous system for the aircraft. If a cable is damaged mid-flight, the wire detects the break instantly and can reroute critical flight signals to a backup path. From smart homes that optimize their own power use to self-healing electric vehicles, the humble cable is becoming an active participant in how our world works. To build a sustainable future, we don't necessarily need to manufacture billions of pounds of new copper and steel. We just need to give the infrastructure we already have the intelligence to do its job.